So now we proceed to the next one. Okay, half-life. There's a lot of calculation here. Okay, half-life. Half-life is what? Half-life actually is talking about the time. Talking about time. Okay, so from just now we know that all the radioactive, they will decay. So during the decay, the numbers of the parent nuclei, okay, after the decay, the numbers of parent nuclei which is not decayed, okay, decrease with time, whether the numbers of the nuclei will increase. Actually, means that the part of the radioactive, okay, it will still remain. So we call it parent nuclei. After decay, there are still some of the parent nuclei still remain, which is they are not decay. And then some, and anyways, it will still decreases during the decay process. But the daughter nuclei, it will be keep increase, getting more and more, right? So means that the original, the parent nuclei, it will getting smaller and smaller, right? Because the decay turn into the daughter nuclei. But means that in the one sample, it's not totally one shot or decayed. Okay, example like this one, we're talking about the uranium. Okay, during this process, all right, let's say this is only the example of the one uranium-234. Okay, so decay become this daughter nuclei. This one's a tritium, right? The 230. Okay, so this is one of the process that will happen, but it doesn't mean that. Let's say an example. Let's say I have the 1 kilogram, 1 kilogram of the uranium-234. Okay, it doesn't mean that when you undergo this decay, alpha decay plus gamma, it will straight away become totally become another new daughter nuclei. No, it's just only a part. So that's why we don't know how much when they will decay. All right. So this process during these periods of time, okay, it will be random and the spontaneous. That's why we call the radioactivity is random and spontaneous. Right? We don't know during the certain period of time how much it will decay. So it means that we don't know. We are able to tell you that after 1 minute, so 1 kilogram will be left only half kilogram, or will be left 900 gram. So we don't know. Okay, but after the long time study, scientists find out that all the radioactive, they have the one pattern. They will have the one constant time, depends on the different type of the radioactive. But somehow they all have the same moment. They will have the constant interval time to reduce half of its initial mass. So it means that this 1 kilogram uranium-234, it have the one constant time. Let's say, let's say after 20 hours. After 20 hours, it will left 0.5 kilogram. But it doesn't mean that after 10 hours, then you will still remain 0.75. It's not like that. It only take constant interval 20 hours, it will reduce half of its previous initial mass. So it means that this 0.5, after another 20 hours, then 0.5 will reduce half, so become 0.25. So we are unable to tell you, we are unable to do the simple calculation. This 1 kilogram become 0.75 is 10 hours. We cannot say so. You cannot say, oh, teacher, 20 hours minus 0.5, only left another 0.5. So does that mean that 10 hours, I will minus 0.25 so I will remain 0.75. You cannot do the calculation like that. If you do a calculation like that, means it will become at the end become 0. This is not the usual calculation by the linear ratio, not like that. So this concept is wrong. You always have to remember, radioactive have the one pattern. They only they will go through half-life, which is the time taken. It will have the constant time taken for the sample of the radioactive nuclei to decay to half of its initial mass. Right. So means that after one half-life, the number of nuclei they are not decay will be half of the initial value. So means that it's easily to say, for the original you have 100%. after one half-life, so the half-life symbol is like this, it's a half-life symbol. After one half-life, so you will left 50% sample. Means that you will minus one half-life will minus 50%. Okay. So then after that, you go to second half-life, another half-life. Another half-life, so 50%, you're going to minus half, minus 50%. So minus 50% of the 50% that you have, then it will become 25% left. Okay. If I use percentage, maybe you're confused. So if I don't want to use percentage, let's say okay, let's say I use original is 1. So after minus 50%, it will be 1 over 2 left. Then 1 over 2 minus 50% again, so you have 1 over 4. Because you're going to minus another half. So when you go to another one half-life, so it will 1 over 4 divided 2 again, so it becomes 1 over 8. So that's what we call timeline. Timeline of the radiative decay. Okay. So during this half-life time, so when and how much it will decay, so we don't know. We only know that after the one constant period of time, then it will be reduced half. Another same constant time, it will reduce another half. This is what we call half-life. Right? So if you look at the module here, so this half-life, okay, we can show into the graph. So from the graph, it will show you the curve line due to the decrease, the half-life concept here. So this curve line, we call it decay curve. This curve line, we call it decay curve. So decay curve, you cannot simply draw. You cannot simply draw any curve line. They say there's a decay curve because it have to based on the concept constant periods of time or the constant interval time to decrease half of its original initial mass. Okay, so why we cannot simply draw any curve? You see, example like this one. Okay, so let's say there is a graph. I'm going to show the numbers or the nucleon numbers, which is the mass number here. Okay, against the time. So when the time beginning 0, right? So I have the original here is a n naught. Original n naught. Okay, so and after that, if I simply draw any curve line, let's say I draw curve here. So this is a curve line. I say that this is a decay curve. So we have to check whether this decay curve is correct decay curve or not. If you say there's a decay curve, means that every constant interval time, it will reduce half of the original. So this height, this one is the original and not. So it means that this one is 100%. So if half, there will be half here. This is half. So here will be 50%. So 50%, when according to this decay curve, you simply draw, you see whether it's correct or not. Okay, here means that there is a time for the half-life. One half-life. Okay, this is a time for one half-life. Okay. After that, 50%, we decrease half. So divided half again. So here, 25%. So there will be the n naught over 4. Here is the n naught over 2. So n naught over 4, you come here. So based on this, that is your second half-life. So now the problem is this second half-life, you see the interval time. This interval time compared to this interval time, obviously they are not exactly the same, which is the second half-life take longer time. When the second half-life take longer time, means that the concept of the half-life is wrong. So you should always showing there is a constant interval time. Then how are we going to draw this decay curve? Right? So you may practice now. You can take out your doodle, try to draw on your paper. Okay, which is you use your ruler, try, maybe example, you draw a vertical line, vertical axis for the 11 centimeter. Let's say you draw a vertical line, 11 centimeter. Okay, and then another one, the x-axis, horizontal line. So maybe you draw about also 11 centimeter, 11 centimeter. Okay, example like this. So 11 centimeter, and then label it. So here is a number of number of nucleon numbers, number of nucleon numbers, sorry. Right, so this one is a time. So, and then use your ruler, get the original or the origin here 0. Use your ruler, you measure 10 centimeter high. Just now you draw 11 centimeter, right? So you measure from the origin here, go up 10 centimeter high, you mark. 10 centimeter high, here is the end knot. After that, you mark also 5 centimeter high from origin, which is a half. So this one, mark it as an end knot over 2. And then you measure again 2.5 centimeter. So you mark here end knot over 4. Okay, and then after that, try to get 1.25 centimeter. 1.25 centimeter, you mark end knot over 8. Right, so with this 3 enough already, we're going to show the 3 half right. Okay, so what to do with the horizontal axis here? X-axis. Right, so you mark AV 2 centimeter. You can make shorter if you want. Okay, or you don't want to mark 1 centimeter, up to you. Okay, any constant interval. So let's say you mark 2 centimeter, you mark here 2 centimeter, every 2 centimeter you mark. So every 2 centimeter you mark constant interval time. So here will be, you can label here as a T1. This one is a T2, T3, T4. So, okay. All right, origin 0. Okay, here there is a beginning, starting here, mark here. And then after interval time T1, so it will deduce for n naught become n naught over 2. So use your ruler. Okay, get the coordinates point. Here you are, this is the one. Okay, the next one, another second half right with the same interval time. Okay, so you mark here. And then third interval time, the half right. So you mark here. If you want to continue another one, 1.25 divided half again. So you got how much? 1.25, 0.625. So you use your ruler if you can get 0.625, up to you. So you just simply mark the half here. Right. If you want, you can continue, but it will become very difficult for you. Right. So you draw and then mark here. Right. Okay. So this one. Okay. After that, so draw the smooth curve line to link all the point here. Try to practice, draw the smooth curve line. Then only you will get this correct decay curve. There's only this one we call it decay curve, because we have the constant interval time for AV decrease half of the original mass, initial mass. So this is a half line. So AV same interval time, it will be the half line. Okay. So that is the concept of the decay curve. When you look at the textbook or either the module, so when the decay curve, we can look at how it's curved, was showing that either there's a higher decay rate or lower decay rate. So if it's a radioactive, take longer time to disintegrate half of the nuclei. So if you take longer time, means that it will have a lower decay rate. When lower decay rate means that the parent's nucleus, it will take longer time to survive. Right? So it means that it will demanding that sample for longer time. So depends on the use . if there is a dangerous radioactive, example uranium, because it will most of uranium it will be have a very low decay rate. That means that during that low decay rate, during the periods of time, it will keep decay gamma ray. Most of the uranium it will decay gamma ray actually, right? So it's very dangerous. But when it comes to the industrial use, if we use for the machine, let's say we put a sample of the radioactive isotope, right? Isotope. So we need the sample to help us in the factory, right? Then this sample we have to choose the radioisotope have a longer half-life, which is we choose for the lower decay rate, so that we no need to oftenly change the sample. But if you choose the radioisotopes to make the product very active, and but we're not going to use it for a long time. Example, we want to inject it into a patient body as a tracer, okay, as a tracer, so that we can scan from outside the body, see whether uh your organs whether it's processed normally or not, right? So because when the example our kidney is processed normally when you injected the radioisotope into body, after certain time the kidney will expel the this radioactive out from the body. So but if your kidney is not working from is not functioning normal functioning, so it unable to expel the radioisotope out from the body. So after a certain time when we scan, it will still remain high dose, means that your kidney have problems already. So this example how we use this as a radioisotope as a tracer. So in this case, because we injected into a patient body, so even example we want to, let's say example that the kidney is no function normally, so it will be keep the radioisotope inside the body. So when you keep the radioisotope inside the body, we don't want this radioisotope will remain in the body for a long time. So that's why in this case we will choose a short half-life, which we will choose some radioisotope that have a higher decay rate, so that after a day the percentage remain in the body will become very less. So we will normally we'll choose a few hours half-life, maybe you choose a 6 hours, because when you choose a half-life is 6 hours, after a day 24 hours it will go through 4 half-life. When after go through 4 half-life, the percentage remaining in the body is only left 6.25%. So and then after another 6 hours, is 6.25% will remaining, it will minus half again, so it will remaining 3.125. So in that case, it will be no harm to the patient, right? So that's why it will be depends on the use of the isotope. So to let us going to choose for the higher decay rate or the lower decay rate, right? So that's an example to compare the decay curve lah. For decay curve, okay, we're able to know whether there is a higher decay rate or lower decay rate. So this question actually come out many years ago lah, in the past SPM. I asked the student to make the comparison between these two decay rates. Right. So as usual, you should know that we have the question, two structure, and the one essay will be asked you to write the answer for the comparison. Right. So that's why you need to know about this. Okay. So for the half-life, problem solving, we have the two different ways to solve. Right. We have two different ways to solve. One is using the timeline, example like this, the way I showed just now, this one, the timeline. We're able to count how many half-life. But the problem is this timeline calculations, this one is only limited for the question that complete half-life. Right. So it means that if the process involved, let's say it's a 2 half-life, 3 half-life, 4 half-life, yes, for this timeline we can easily solve. But if the process involves 1.5 half-life, 2.1 half-life, so the cases like this with the timeline problem solving solution method like this, we are unable to know. We are unable to know that it's a 2.5 half-life or 2.3 half-life. Cannot. We have to use formula. Okay. So there's a new it's new in your syllabus lah, right? They bring back against this formula. Okay, so this formula they bring back again back to the syllabus, because previously in KBSM the last after 2016, they removed that. Before 2016, they still remain this formula in the syllabus. But after 2016, they removed that. Now they introduced back again. Right. So this formula it can use to knowing about the half-life is incomplete. Right. So it means that it's let's say the 2.3 half-life, 5.4 half-life, something like that. Because based on calculation, we're able to know how many half-life exactly. But the timeline we cannot solve. Okay. So later we see how to use these equations. Okay.